I'm Larry Olson with Olson Engineering, Chief Engineer and President. This is Jared Lowe, our Senior Project Geophysicist. And we're both going to be speaking today on geophysics and non-destructive evaluation of rigid and flexible pavements and slabs on grade. So don't need to belabor this. You could just read it. The company started in 1985. We specialize. Is still a problem with the chat?
Is the audio still working? Just making sure. Yeah, I wonder. Okay.
Works for me now. Okay,
All
we're
right.
good. So, and we have been selling instruments for testing concrete, asphalt, masonry, wood materials of structures, pavements, foundations, and some crosshole and downhole seismic systems ever since. So our branch office has a couple of people in Rockville, Maryland, Washington, D.C. We work all over the country internationally as engineers and geophysicists, geologists. Range of our consulting services are just listed there. I don't need to dwell on them, but you can see them. We also do load tests and structural health monitoring of bridges and buildings. We give our own training seminar. It should happen basically in probably early October this year on non-destructive evaluation of structures, pavements, and foundations in geophysics at our headquarters in Denver, Colorado. And also myself and Dennis Sack are involved in ASCE courses as it lists on teaching those. So this is for the basics, and it should be animated. If you've not looked at seismic waves and body waves, in particular, this is a compressional wave, the sound wave we're speaking with. It pushes and pulls as it travels. The shear waves or secondary waves have a shearing action transverse to the direction of propagation. We use that in some of our testing, not so much going to talk about that today, but in some imaging of flaws in concrete, we use it. And we will be talking a fair amount about surface waves today, so-called Rayleigh waves. And the motion of the particles is kind of rolling backwards in a retrograde elliptical motion, attenuates with depth, but it has some unique properties and is 10% slower than a shear wave. So they do all relate. The elastic wave velocities and modulus relationships are listed here. Speed is simply the distance divided by travel of a compressional P wave, primary wave, or shear wave. And surface wave velocity is 9/10 approximately in most materials of that of the shear wave velocity. Shear modulus is listed where it's a function of the unit weight divided by acceleration due to gravity times the shear wave velocity squared. And Young's modulus equals to 2 times 1 plus Poisson's ratio times the shear modulus. And Poisson's ratio is listed there as well as a function of the compressional and shear wave relationship. So the energy, interestingly enough, is when you impact the surface, the weakest wave is the compression wave, what we use in some impact echo testing. 26% of the energy goes into shear, and 67% goes into surface waves, and that's important in some of the tests. It's dominant, although the slowest wave, and it exists at the surface. So the outline for today is we're going to talk about scanning impact echo and applications to pavements and slabs. And this is for pavement to slab thickness, debonding, delamination, raveling, and honeycomb. Ground penetrating radar for subgrade voids, typically ½ inch and greater in thickness is more detectable, and pavement layer thicknesses. Not only the surface pavement layer, but the underlying road base and subgrade. There are the dielectric contrasts. Slab impulse response method for thin subgrade voids. We often do that in combined with ground penetrating radar on rigid concrete pavements and slabs, because it's sensitive to very thin voids, which nonetheless still take away the subgrade support. And scanning spectral analysis surface waves for Young's moduli and condition of pavements. And scanning something newer that we're going to talk about, multi-channel analysis of surface waves, which is not newer, but that being done with microphone arrays is something you may not have heard much about before. For looking at Young's moduli and thicknesses of pavements, as well as reaching down into the road base and subgrade. So the first case history is showing what we developed for scanning decks originally, but it also has applications on scanning both asphalt and concrete pavements. And we put a pair of these rolling sensor wheels in the wheel paths of 42 lane miles of interstate highway jointed concrete pavement. We have to go slow because we're testing every 6 inches and impacting the concrete with a solenoid. They're all, so we get a test here, 6 inches, it rolls 3 inches, we get a test on the right. So we can take a lot of data, even though it's going slow. It took about 12 days with traffic control, of course, to cover these 42 lane miles. And when you look at it, the basic impact echo method, if you haven't seen it before, is you impact the surface and you look for resonant echoes from flaws or the thickness of the material. And the depth of that echo is equal to a shape factor, which in a flat slab or pavement shape is 0.96. It's a lower number for multiple resonances in beams and columns, but it's basically 0.96 times the speed of sound, the compressional wave, divided by twice the resonance of the frequency of the echo. So, assuming your concrete was nominally 12,000 feet per second with a factor, a 6,000 hertz echo corresponds to 1 foot depth, 12 inches, and twice that frequency, 6,000 hertz or 1/6000th of a second for the resonant echo to occur, would be a 6-inch echo. So, having said that, is kind of a lead in to showing you the solenoid here, and there's a thin tire over those relatively heavy wheels to keep in contact with rough asphalt and concrete surfaces, and a displacement transducer with some springs behind it that contacts and puts the weight to get good contact, hit the concrete sharply, and get the echoes. So every 6 inches as this slowly rolls, hitting left and right, we're getting data out of each pair of wheels. So this shows an example result. The problem on this project was that they, within a relatively short time of placing the concrete, experienced cracking at the joints, and they're associated with the dowels. And so when we were scanning it, here's an example of 520 feet of data with tests every 6 inches. This main echoes are around 12 and a half inches thick, which is the thickness of the concrete pavement, and it's jointed. So every 15 feet, there's a joint. You can see that at some of the joints, there are these nominally 5 to 7 inch deep echoes, which is basically the depth of the dowel joints. And so here's an example result where it's the normal thickness, that's the time domain, time versus voltage, and the resonant peak, where this is 0 to 50,000 hertz, is showing 6,738 hertz, which corresponds to 12.46 inches for this velocity of the concrete, which is typically between like 12 to 13 or 14,000 feet per second. It varies. And you want to calibrate for that based on a known thickness. But this is showing the damage. So another example result is now showing this area where there were several echoes for like 3 feet or so of the dowel lengths that shows a much higher frequency of resonance echo at 13,477 hertz corresponding to 6.23 inches. So with this information, we were able to map out, and it's shown in red, the outside and middle lanes were the worst, and the inside lane was generally in better condition. But you'll notice how it's happening at the joints. And so basically what occurred was, unfortunately, if you don't cure the concrete properly, it can curl or warp. Uh, because the top of the concrete, if it's not properly cured, will curl up because it cures faster and shrinks more than the underlying concrete against the road base, which cures a little better. So that results in curling and stresses, and that's what caused the dowels to literally crack the concrete, kind of like a delamination in a bridge deck. So we were mapping this all out so that they could look at repairs. So with that, I'm going to turn it over to Jared to talk for a bit on ground penetrating radar and some other things.
Yeah, hey everybody. So similar to our impact echo wheel scanner systems, you can also use GPR to scan spans of roadways at a relatively quick rate. Normally we use GPR for geologic purposes and geophysics, but it can also be applied at higher frequencies for roadways. These are a couple examples of some of these higher frequency systems just dragged behind or towed behind a vehicle, and typically they have an odometer to tell you when to scan, when to pulse, as well as your location along the road. So GPR operates on the function of differing dielectric constants. So when your electromagnetic plane wave reaches a new layer that has a different dielectric permittivity, different dielectric permittivity or constant from the previous layer, that's when you'll get a reflection off of it. And so here's a few examples on the right of different dielectric constants for different materials. Relevant to this presentation, you look at asphalt and concrete, which are on the order of 8 to 10. And then we've had experience with different concretes, and those might represent different dielectric constants. It's usually important to try to calibrate your data so that you have accurate depths. And you can see on the top left, depending on that constant, you get a different velocity of your electromagnetic plane wave and thus a different depth. So here is an example B scan of GPR data. This is comprised of multiple pulses along a roadway, and we are able to interpret different layers. So you can see the very first pavement layer as well as the base, and then you hit the contrast as you go into the subbase or soils beneath that. So in a lot of software, this is Radan, but a lot of software lets you pick layers, whether that be horizons or individual points. And you can use these interpretations with other methods, such as impact echo, for interpreting and visualizing your results. So this is a case study for an entire bridge where we collected multi-channel GPR. And so you can see on the bottom here the full extent of the bridge and the coverage that we did. And this was using Contour Radar's 19-channel GPR. So this has a swept frequency spanning, 200 to 3,000 megahertz. So it's able to get a better visualization for different depths. And yeah, you can drive up to 20 miles an hour with this system. It's coordinated with GPS. I believe there's an odometer that's hooked up to the back right wheel. And yeah, so it's able to get a swath worth of data using all 19 channels. So you don't have to drive so many times with just an individual single channel system. They have their own proprietary software for this, but you can also process it with Geolytics, which is a cloud-based software that we typically use for a lot of projects. But yeah, 3D Examiner it was very useful. I was helping with the processing and the plotting of these. I wasn't there for collection, sadly, but you can see in the bottom right that they have a map view, as well as your B-scan view, an individual trace view, a swath view in the bottom left. So their software is actually really good for the multi-channel collection. And so once you've processed it and picked out all of those individual points of rebar, you can make maps such as this one. So this one is showing the top of steel, the very first layer of steel rebar, and it's been interpolated so that you can see just a plan view of where you might have deeper layers, whether that be due to extra asphalt on top of it or due to inconsistencies just with the rebar mat. Here's just another example of picking that top layer of steel. It's mapped out with this blue line here. And then above that, we've also picked, I guess that's just time zero, but you can also pick the asphalt surface. Yeah, so asphalt surface and asphalt bottom before your first layer of bar. And so on the bottom side here, you can see just another visualization of the bar and how you might get different patterns depending on joints, etc. And then, yeah, lastly, for this project, they mapped out a bunch of different features, whether that be distance to the first layer of bar, distance to the bottom of the deck, and we compiled a bunch of these different maps for the client. Another example of what you can do with GPR is its use case for voids. So in North Carolina, we took our lower frequency 70 megahertz and 300 megahertz combined system from Impulse Radar over this area where they have water leakage coming up through the cracks of the road. They had installed these water lines that go transversely across the road and were observing a couple defects, I suppose.
Horizontal drill.
Yeah, horizontal drilling. And so we took GPR scan lines across the roadway, of course, with traffic control. I think this was all night work. Maybe not on the frontage roads, but regardless, yeah, scans every 3 feet on the frontage roads and the main highway. And yeah, we were able to see some pretty stark features here above the cast iron water pipes. You can see the water pipes marked by these purple dots, as well as, these very ringy responses, as well as high frequency, or sorry, high amplitude response underneath this red line on the left. And yeah, we were able to map it all out in plan view, so we can see the water pipe going across the entire road, as well as where the defects might line up with each other. And yeah, here's the photo of it. They cut through the asphalt in the roadway and discovered this giant void from water washing out material. So it's just a really good example of GPR working, being confirmed, and us being able to correlate, where these bad areas are for them to fill and grout to repair the roadway. So going into another case study where we combine multiple methods, this was pinpointer GPR as well as our S-cubed system operating both as impact echo, as Larry was describing previously, as well as SASW, spectral analysis of surface waves, which I'll talk about here. So this method uses two receivers instead of just one, and then instead of a solenoid source, we're using a hammer to impart somewhat lower frequencies, but you have a wider frequency range using one of these ball peen hammers. So here's our instrumentation. On the left is our Freedom Data PC, which we typically use for these projects, and you can type out your file names or whatnot. It uses Windows 11. On the right is a handheld system, which we are currently revamping. And then the middle is our receiver setup. You can change the distance between your receivers. Um, and so here's your typical response from it. So your time domain records, similar to impact echo, you get a strong first impulse, and you can see you get surface wave response. You're typically hitting on the first receiver, which is why it's usually stronger than your response from the further away receiver. And so you look at the phase after I guess I'll go back here. After you've chosen a very first initial starting point for this, you look at the phase between the two responses at every frequency. So you take a FS and you look at every frequency and what, I guess, phase difference you have between them. So if we're looking at the first phase cycle from 0 to 360 degrees, we would see that that intercepts at 2628 hertz using a 2.62 foot SASW bar spacing. You can approximate that that's 6,900 feet per second. And so if you carry that on to all your other frequencies, you can see that the phase is actually not changing. The cycles are staying the same, which means it's really sound concrete. You won't really get this data in the field, but yeah, we can see that when we unwrap the phase, you can get a constant 6,900 feet per second response for this sound concrete. And so from the spillway, we have a couple examples of really good concrete. On the right here, the very right side of the plot, you can see we have 8,000 feet per second, pretty consistent through the entire slab, just consistent response at that velocity. And then on the bottom left, we are mapping the impact echo just from one of the sensors, whichever sensor is closer to your impact. So you can map out the resonant frequency, and we see that here for the sound concrete, it was around 12 inches. And I think that was the expected response. It was either 12 inches or 14 inches. But yeah, the SSW and the impact echo from this were really good. Here's an example of a poor impact echo response for that spillway. And we have a resonant frequency of 14,000 hertz, which corresponded to closer to 4.8 inches. And so there's a delamination through most of it. Um, I think it was just cracking due to a thin layer of rebar there that was getting corroded. So the entire spillway ended up looking pretty delaminated. And on the right is a lower velocity response, around 6,000 feet per second. You can see the cycles are a little bit closer in this phase plot in the bottom middle. And so that just shows that this would be a good example of a poor response. So mapping that all out, this is a orthomosaic overlaid image. I think the client ended up taking drone data and stitching all the photos together to make this look pretty. But we mapped out our impact echo results from on top of it. I think we took data over a 4 foot grid. But yes, there was a lot of delaminated response here. I mean, you could see chipping out and spalling through the entire slab. SASW can be plotted in terms of a slice, similar to GPR. You can take at what depth, what velocity you get. So this is at 3.25 inches. We get relatively sound conditions, anything above 6,000, 7,000 feet per second. We usually consider sound. And then below that, you have weaker concrete, lower velocity concrete, which is usually relevant for these types of projects. Similarly, we can plot out GPR as a slice. This slice, I'm taking an average between 1.3 to 1.8 feet and mapping out any high amplitude areas. In this case, we weren't looking at voids with the GPR. We're actually looking at, I think the slab is pretty much directly on top of bedrock. So it's wherever bedrock was. We're kind of mapping out that area to see if there's any correlation between delaminated areas or weak velocity areas based on bedrock. I don't think there was much correlation here, but it was just an interesting study to take GPR, impact echo, and SASW over the same region. Yeah, and I'll pass it back off to Larry to talk about slab impulse response with GPR.
Okay. Thank you, Jared. So just continuing, we've often found that there are slabs on grade and where there are thin voids where radar doesn't detect it as well. So we combine slab impulse response on a point-by-point test grid with ground penetrating radar, which is scanning on 2D lines. And this can be done on tunnel liners, pipe walls, spillways, roadways, building slabs, other rigid pavements. So the impulse response does have an ASTM standard of C1740. It consists of an instrumented hammer. It's a modal vibration test. It's similar equipment is used for sonic echo impulse response is a modal vibration test for deep foundation integrity and links. And basically, here's shown a geophone, or if you're at an angle, geophones should stay within 10% grade or less because they're normally designed to work flat. So when you have angled, you can take an integrated accelerometer. It's still a velocity transducer. So when we hit the slab, we measure the impact force and we measure the velocity response of the slab to the impact. And it's when it's more flexible because of void, less stiff, it moves more, it's a higher mobility, and we can tell that loss of support, even to less than a 16th of an inch in thickness. So it's very sensitive to thin voids. So this particular case history was at a mountain reservoir in Colorado, and they knew they had some voiding issues below it that they wanted checked out, and there we're doing impulse response testing on it. It was basically 6 to 14 inch thick concrete. You have to keep that in mind as you're evaluating the data, because if it's thicker, it's going to be stiffer in general compared to a thinner slab. But the response is still different in that when you have voids below it, it tends to ring and it's much more mobile and more flexible compared to the same thickness of slab with good subgrade support. There was observed water seepage at the joints. They'd done a little bit of drilling, prior hammer soundings. They seemed to think they knew they had some voiding problems. So this shows when we did the GPR, it was fairly steep at the upper part, and we had on some felt bottom shoes and backed our way down with a GSSI 400 megahertz antenna and a distance wheel to take the scans. And this shows the scans of the upper spillway versus then the lower spillway, which was flatter. And we did wear these felt bottom shoes that are typically worn by fly fishermen to have good footing in the Colorado streams when they're fly fishing. So this shows some GPR example results. The basic thing we were looking for here in showing void up is the reflection amplitude. And that's a function of the dielectric constant of the upper material, which is concrete, to the half power minus the lower material, which in this case was generally an air-filled void, divided by the sum of the two. And so the math works out that and this was a fairly high dielectric because it was a spillway, it was moist concrete. And so relative dielectric in air, speed of light, is 1. And the soils, we took it to be around 4, the nature of the rock and minor soils that were below it, mostly rock. And the reflection coefficients vary from 0.52, 52% of the energy reflects, versus 22% for the soil. So the bright spots in this scale are voids. And you can also see the rebar and how it's going up and down a fair amount. This is time in nanoseconds. This is depth in feet. And so you can see a lot of the spillway is basically varying between this 6 to 14 inches. This particular scan is the lower part, the bottom 35 feet. So this is another project. I included this because if you have a water-filled void, or people always ask, well, can you tell us the thickness of the void from radar? Generally not, because you just lose too much when it's an air-filled void at the two reflecting boundaries to hope to see the thickness. But in a water-filled void, the dielectrics are more favorable, and we could see both the bottom of the top of the void and then deeper, the bottom of the void. And that's because it was filled with water. So that's a little unusual. Most time we don't see that. So the slab impulse response was done on a 4 by 4 foot grid, sort of matching the 4 foot spacing between the continuous scans, 2D scans, or so-called B scans of the GPR. And so we did all this testing. Um, this is showing a hammer blow. It's only a couple thousandths of a second. It's calibrated. That's about 5,000 pounds force from a hard plastic tip. But this is a ringing signal. If this was a good support area, it would have gone down and up and damped out quickly. When it's ringing like this, it has an effect on the processing the data into the frequency domain. So the upper one, where this coherence near 1 is just good quality data from nominally 20 to 1,000 hertz, that has a function of signal to noise ratio. And it had a good subgrade support with good so-called low smooth mobility. So what that means is mobility is inches per second. That's the velocity response from the geophone, or in this case, velocity transducer because of the angles, divided by the pounds force of the impact. So this is a modal vibration test. By comparison, an area with poor subgrade support was much higher mobility, very irregular response, not well damped, the coherence drops off. So very dramatic differences between this. And you basically end up, for a given project, kind of grading it between good subgrade support, normal, questionable subgrade support, and void or poor subgrade support. So when we compared everything, the GPR being parted in the dark colors indicating more void areas, the two sections of GPR just stacked on top of each other here, versus the slab impulse response relative mobility results, where we normalize this to the mean value, counting for somewhat the variation in thickness from 6 to 14 inches. You can see that, okay, the mean was here in these colors, and then the void and high mobility areas went into the blues. And so you can see and into the reds, et cetera. So when we suggested coring, the small dots found void thicknesses from 1/2 to 1.5 inches, then larger circles 1.5 to 2.5 to 3.5 to 4.5 inches of voids were some of the largest and thickest voids. So we did a little further checking. We got a borescope that was very good. This one is, you can actually, it's normally used to inspect power turbines because you can literally with a joystick drive it and go into the voids and poke it around and look at other areas. So we found that there was very good correlation. Extensive subgrade void was found in these core holes, and we helped to further confirm the thickness variations by doing this. So it was a good combination of the two methods. So shifting gears a little bit, because we're going to talk about using some of these methods to look at surface waves primarily, conditions of asphalt pavements. Can also be applied on concrete, but we're going to focus on asphalt today. So back in the day, I was a student of Ken Stokey's at the University of Texas at Austin. And in fact, my office mate started working as a master's on the spectral analysis surface wave method in graduate school. And then Sohail Nazarian and subsequent PhD students really ran with the method under Ken Stokey and Dr. Jose Rosette. But what Marwan Awad did, who worked for us for a number of years, and he did his research on looking at the so-called TTI Annex, which is at Texas A&M University, the Texas Transportation Institute, had a variety of asphalt pavement sites. And so he tested it with an ultrasonic pulse velocity source, high frequency of 50 kilohertz, going at 30 degrees freezing to 80 to 97 to 143 degrees. You can see what happens. These phase cycles shift to the left, and you lose when it gets very hot. You didn't lose all the data, but you only got up to around 20 kilohertz because it was so attenuated by the asphalt being relatively soft. And as the cycles shift to the left, it's much slower velocity. That's what's shown in this plot. This is a log scale of wavelength, and wavelength is approximately depth, but it was nominally 0.2 inch thick asphalts, 0.2 meters thick asphalt sections, which is nominally 8 inches. And you can see how the velocity varied a lot from like 1,700 meters per second when it was near freezing to, as you got warmer, dropping down at 142 degrees to 1,000 meters per second. Well, since velocity squared is directly proportional to Young's modulus, which pavement engineers use, this means it's a lot less stiff. It's a lot lower modulus as it gets hot. But you'll notice it drops at about the same depth in all these locations, which is showing the thickness and going down into the slower velocities associated with the road base. So I mention this because when you do testing of asphalt, you want to record the temperature because you'll end up normalizing the modulus with temperature and have a relationship for different frequencies and measurement frequencies, typically ending up around room temperature 70 degrees is typical. So, and that also relates to laboratory testing you can do on asphalt specimens as well, such as resilient modulus or resonant column. So we were fortunate to be involved with the SHARP 2 R06D, that's the Strategic Highway Research Program, Phase 2, study that was funded for delamination of asphalt pavement lifts. And the National Center for Asphalt Technology built test track sections with varying conditions under Dr. Michael Heitzman was in charge of the research. We used our sonic surface scanner cart, this is an earlier version of it, to test the asphalt. And here's Ken Mazer of InfraSense, who was also involved in the study as a consultant. And our Dr. Yajad Tinky at that time has retired. But they were doing the testing on this test track. They normally at the test track, it's 2 miles long. And on the main lanes, they're running trucks like 5 days a week, 24 hours a day over a 3-year period to evaluate new asphalt mix properties and how well they work for DOTs who fund the studies. But this section was not so large. It was 250 feet long. And we did some impact echo scanning on that. One section, here we're going over this length of 100 feet, walking through it. The whole total section was 250 feet. But right here, it's showing some echoes, and this echo is showing up very nicely, that it's picking up the depth, and it's nominally right around the 5 inches or so where they had constructed a known debond or delamination. So this first section, test section 1, half of it in gray was baghouse dust, and the other half was thin paper. We kind of joke about it. It's difficult. Say a contractor has a dust storm or something happens when they're placing an asphalt pavement and they lose bonding between the lifts, or the tack coat simply doesn't take and they lose bonding. Well, that's a lot weaker pavement. And it's quite a concern on a new asphalt pavement because when the trucks break, they will shear the pavement at that debonded, or it was called in the research, delamination depth. So the baghouse dust is more like a dust storm. It was hard to make the thin paper always not be ripped by the paving. So that was a challenge. And I kind of joke that it's difficult to build perfect defects in research that a contractor can do without even trying. So this was at 5 inches deep. And some impact echoes showed up. We found those delaminations at this 5-inch depth in the range of 4 to 6 inches. And they're in the red colors here versus the deeper section of the overall pavement. So that first section, again, just in a grayscale plot, going from 3,000 feet per second for the velocities of the surface waves up to 5,000. You can see at 1/10 of a foot, it's fast. 2/10, it's fast. 3/10, 4/10, it's slower. This is picking up on that 4/10 of a foot is 4.8 inches. That's picking up on the slower velocity associated with the simulated delamination of baghouse dust or paper. And it stays slow below that in this case. So when we looked at it, what did we see? So sound asphalt was basically around 5,500 feet per second to 5,000, going in 0.8 of a foot. No variation, velocity versus wavelength, where wavelength is approximately depth. But in this area, which was a thin paper delamination, we saw a distinct drop in velocity from nominally 5,500 to 6,000 feet per second down to 4,400 or so feet, 4,300 feet per second. And this drop in velocity is right around the 12.5 centimeters or 5 inches deep. So it's happening here in the wavelength scale around this 0.43 feet. So that drop in velocity is because there simply is not good bonding. Even though there's contact because of gravity, the simulated thin paper broke that bond and it's slower across the interface. I think of it as weak springs connecting across a joint or the delamination, in this case, the asphalt lifts that were not bonded. And similarly, when we check the baghouse dust, very similar results, 0.4 of a foot, 4.8 inches, dropping from 5,500 feet per second down to, again, around 4,300 feet per second, showing the effects. And we also were able to find with high frequencies were generated in the surface waves, the 2 inch deep drop in velocity as well, from nominally 6,000 down to around 4,800. So from this information, we were able to plot up for the whole test section at different depths. And this is going, it's a little hard to read, but the top one is at 2 inches, 3 inches, 4 inches, on down to 10 inches deep. And so there's various flaws picking up in various areas where they had built these defects, the simulated debonding. This is a raveling section. The very bright red one is much slower, where that is stripping. In other words, they took some recycled asphalt pavement with no bitumen in it, about an inch thick, and put in a raveling section. And so that showed up quite well as a reduction in velocity also. So we've gone on to do some demonstration of this scanning for DOTs as part of the project for an implementation assistance program. But we also have participated, that's our Pat Miller. He's a associate principal engineer, vice president with our company that is doing scanning at the Minnesota DOT's test track, which is part of the National Road Research Alliance also. They coordinate that meeting that's coming up the end of April with our sonic surface scanner. And it has the GPS on it, the two rolling wheels, where the wheels are lined up to get an impact echo test on the left and 6 inches apart surface waves between them as it slowly rolls and impacts every 6 inches. And we're just walking a mile an hour. So we did this scanning on this. They had built these raveling test sections in their test track of the asphalt pavement. And we're picking up these slower velocity areas in the thicknesses that are coming out of impact echo. Then we're also in the surface waves getting the slower velocities. And this shows particular some where the raveling is more distinct at greater depth, picking that up as well. So we're mapping this out with the surface wave approach. And then just one way to look at the data, you can subtract so-called z-score, the mean from the raw score, and then divide it by the standard deviation that helps to make it jump out in terms of plotting where these raveling sections are. So now I'm shifting, and that was just another example of the z results, the z-score. So the Minnesota DOT has funded this raveling study now. Earlier, excuse me, let me get this correct. This study was a bit earlier. This was another pooled fund study where DOTs contributed funding that was done from 2020 to 2022 for a seismic approach to quality management of hot mix asphalt. And so this uses multi-channel analysis surface waves for Young's moduli and thickness of the HMA pavement. Their goal at that time was a straightforward one, in that on a new pavement, they wanted to be able to determine the modulus and measure the temperature to see if it met what they thought it should meet for good compaction and good properties. But pavement design has shifted to a mechanistic empirical pavement design approach. And what that means is engineers are now using Young's moduli to design their pavements. So it's important to know it and measure it and check it versus what you predicted from earlier laboratory testing. So basically, they were, and this was done by Chun Park as a principal investigator. We know and work with Chun Park and use his software for some time. It came out of Kansas Geological Survey and helped originate the multi-channel analysis surface wave method for seismic that is shear wave velocity determination with depth from the surface, building on the earlier spectral analysis surface wave study, but with multi-channel geophones, typically 24 or more geophones. So this study was done by generating surface waves at 20, 25-mile-an-hour speeds with a bouncing bolt head on a zip tie with 4 arrays of 16-channel MEMS microphone. We also have worked with Niels Ryden since the mid-2000s. He was a researcher with a pavement group. He's become a professor as well as involved in continuing research on pavements and using surface waves. So he's been worked closely with Chun as well as his associate, Josephine Starkhammer and Jin Park. So they were looking at this system and prototyping it with National Instruments technology. With the arrays, you can kind of see them there. A little better picture is here that shows them being taken at the back of the vehicle, suspended with 16 channels of closely spaced MEMS, miniaturized electronic microphones, that are at angles left and right and at angles at a bit of an angle off the back. So they were going down the road with the bouncing ball. And I'll illustrate early work on that. This just shows some Swedish work that Nils had done earlier. He started researching microphones back around 2004 or 5, and they were just bouncing along with the array in the middle there and suspended. What they ended up using that worked surprisingly well, a little erratic, was a zip tie. And when you go that fast on a rough asphalt pavement, you get a lot of energy put in every 3 to 5 feet. We're hoping to use solenoids or some other mechanical source in the future to make this a little more controllable, but the basic idea was developed there. But they were only looking at the first, say, 3 or 4 inches. That was their main concern. They weren't trying to go full depth. Now, why does this even work? Well, as you would guess, when you hit it, the surface, you get a direct airwave that travels at the speed of sound, nominally 350 meters per second. That's like 1150 feet per second. And the microphone senses that. That's a lot of energy. That sound wave is sensed by all those microphones. And so when you look at the raw data, but at the same time, you also generate surface wave energy in the concrete or asphalt. And as long as the concrete or asphalt is faster than the speed of sound, and it will be, you can see what's called a leaky surface wave or a leaky Lamb wave that emits from the surface and gets there faster and is ahead of the direct air wave. Now, earlier work, they measured directly with accelerometers. Niels' earlier work had an accelerometer that he would measure the propagation of the waves with. So the advantage of the microphones is obvious. Now you can start to drive faster. You can certainly do it faster on a cart. You don't have to have a contacting sensor. You can pick it up with these MEMS microphones. So what do you see? There's the surface leaky Lamb wave is very weak. You can see it's there, but it's very weak. And this is just time and the channel number. But the direct air wave is very strong. So when you process it into the way similar to SASW, but it's phase velocity versus frequency, not wavelength in this plot, velocity equals frequency times wavelength in surface waves, that's the velocity of sound, 350 meters per second. You're dominated by that. But digitally nowadays, we can mute the data. Muting it means you literally put in a bunch of digital zeros to get rid of the airwave energy and leave the strong surface wave energy, which shows up well when you do that. And then you get this velocity of 1400 meters per second after airwave is muted, and lower frequencies go down into the effects of the slower velocities of the road base and subgrade, which can also be modeled and determined. So the first Seismic 24 data, which is what the new system is being called, moving on from the National Instruments laboratory type approach to a more commercial system, very good raw data. There's still strong airwave. You have to mute it, and then after it's muted with high gain, you can still see other things. But there's so-called antisymmetric fundamental modes and symmetric modes. Niels Ryden has looked hard at this, as well as Chun Park. And it's helped to model all of the different layers as well in some of Niels' work. So some of the early results, we're showing this velocity of 1500 meters per second from frequencies of, say, 10,000 to 30,000 hertz. And then getting estimations of how thick it is, of 6 to 14 centimeters, different thicknesses of different layers in doing this. So now our company, Olson Instruments and Olson Engineering, have joined with ParkSeis and Seismic Source, who makes seismic data acquisition units is and ParkSize is the software. It's called ParkSize X. So this is an effort to commercialize it and make it available to people. And so what you see in that, sorry, got away from me. It's hopefully might be a new prototype vehicle mounted system is sometime this spring, maybe as soon as the end of April, where you would have some sort of bouncing source and 24 channels behind a truck mounted on a receiver of some kind. But right now, what Seismic Source did, and this was demonstrated in a seminar we participated at in last October at their offices in Ponca City, Oklahoma, that they got these commercially available bike carts, adapted them, suspended the microphone array below it. They started off with a hand-operated steel ball impact source. We brought along one of our solenoids, mounted it on there to automate this more. And on a cart, solenoids work fine. We may have some challenges with that going 25 miles an hour because you can get it caught and ripped off, et cetera. But we hope we can overcome mechanically in some way those challenges. But then we also went outside, and there's Jared. I was also out there, but there's Jared testing with Paul Martin of Seismic Source on their asphalt parking lot with this large solenoid source. So we got these results on the concrete floor slab. It was 4 inches thick, good velocities. You can see nominally 4 inches thick, and velocities on the order of up to 2,400 meters per second, and a little slower as you get into the probably sand bedding below it, down into the much slower natural subgrade soils that they probably just compacted inside their building. And that's where that scanning was first done, and you saw it there. So I have a touchy mouse. This shows.
It's ready to go. It's ready.
Okay,
Yep.
let me see this thing. This is when we did a seminar recently. There's the seismic source microphones. There's different solenoids. We have mocked up a foldable cart. This is a prototype. We're making a new foldable cart to be able to ship it, but it's just rolling and impacting, pulling the solenoids. It was done at the SAGE meeting, the Geophysical Engineering meeting in Pittsburgh recently, as a seminar that June Park organized. And we were just testing through a tile floor slab. It worked surprisingly well. We got good data where it was bonded, tile over concrete. So, and this is just a little cart with 3 different solenoids in the cart. Let me stop this. I'm talking over myself. So here's our different solenoids, but in this little cart behind it, there are 3 different solenoids, and we picked the medium one for this demonstration. And there's just a picture of the underside of the microphones, which are every 25 millimeters for about a 2-foot length. So that's testing on our floor slab here in Colorado. You can see where the velocities are higher. It worked well. So in concluding the talk, the Seismic 24 testing is planned, and maybe the vehicle mounted if it's ready, for the Minnesota DOT's National Road Research Alliance test track meeting on April 30th, and it's on those raveling stripped areas. So we want to see how well it works with an MASW approach for analyzing these defects and mapping them versus the pair of transducers we used in our slower rolling surface waves. You can walk the microphones easily 4 miles an hour as you go because it's so much faster in couples. But the ParkSize X software that Chun has been developing provides the thickness and shear wave velocity profiles, Young's moduli, Poisson's ratio for asphalt and pavement layers, as well as the underlying road base and subgraders. So I want to thank you very much for any questions. If you're interested in any technologies, we certainly are helping to commercialize and sell the Seismic 24 type systems. And with that, I'll pause and we can check the chat and see if there's any questions or if somebody wants to simply state a question. Okay. So did we tell you too much, or does anybody have any technical questions they would like to ask today? Both Jared and I are here to answer them. So Billy Oliver has put in the chat, how sensitive is the microphone technique to road noise? Can you run it with traffic in the adjacent lane? It's not a big factor because you get quite a bit of road noise just from the vehicle itself. But if you get, and the frequencies of the road noise is going to be lower frequency, probably under 100 hertz versus the high frequency of the testing. But it can certainly cause some problems if it was like really noisy. but it's not been a big issue so far. Also, keep in mind that you are taking quite a bit of data, and if you're doing it with a cart, you probably have traffic control, and so you're a little bit away from the noise. But good question. And you're also trying to mute it. But definitely part of the desire of getting the solenoid working or some controllable mechanical source that can go 25 miles an hour is that you can know when you want to take the data. So you get the right snapshot, which also minimizes noise effects. Okay. Are there any other questions? We're excited about the seismic technology because we think it'll have applications on concrete slabs as well. And if we can get up to the 25 miles an hour and test fairly close together, it might to be able to do some good defect mapping. And that's part of the purpose of going to test at the MnDOT's NRRA event in their test track. Okay. Yeah, I've worked some with the software. Jared has used a lot more. I'll let him talk about the data recovery and analysis. Is it loaded to a cloud, automatically geolocated?
When we're talking about our other systems such as GPR or the S cubed cart, it's not very well plotted in our own software. We typically take the data out to QGIS to plot it. And likely that will be the same case for the seismite cart. But yeah, we just do that in-house ourselves.
It doesn't go up to the cloud during testing. It's definitely on a local computer.
Right.
It's a
So
Windows computer.
you will pull the data back at the office.
It is relatively fast processing.
Right. If you're using Geolytics to process data, that's when I mentioned that data we upload to the cloud and process it there, because that processing can be rather intensive once you have so many lines worth of data. It's often faster if it's done on their servers.
But in the seismic system, you're going to do it on just a good Windows computer. And it doesn't take so long to process it. What do you think? Typical file depends on their length.
Yeah, I mean, it only Tune Park is trying to automate that processing for us. So as soon as you collect the data, it'll take 2 seconds to run, and it'll give you a 1D plot of whatever sample you just took. And it tries to interpolate in 2D as you continue to collect data along the roadway. So the ultimate hope is for you to have real-time data analysis and geolocation, but that's still a work in progress with Tune Park.
Yeah, it doesn't take too long after you finish, even if you put it in post-process batch mode to just run it.
Yeah.
For the automatic analysis.
Yeah.
Okay. Thanks for the question. So thanks for the compliment. Hope everyone did enjoy it. Like I say, if there's any other questions, we're happy to answer them. But we will upload it. You can share it with other folks. It will be part of our regular YouTube thing. And we're happy to provide microphones. If you are interested in instrument quotes or consulting services, obviously we'd be happy to work with you on that. But I think this is going to be an important step forward for asphalt pavements in particular, but also maybe on extending into concrete decks where surface waves could be useful. But in particular, it's going to be useful for asphalt pavements in characterizing the Young's moduli, as well as the thicknesses and to a reasonable accuracy, the underlying moduli of the road base and subgrade. That's something we're still experimenting a bit with. We'll learn a bit more from Minnesota too, in the testing that will be involved in the end of the month. So, are there any other questions? We're about at the end of our hour time frame. Okay. Well, if there's no other questions, we'll follow this up with an email and link to the talk and all that. We do want to thank everybody for attending today, and you all have a great day as well, and look forward to hopefully hearing from you in the future. Thanks. Appreciate everybody's thanks for the presentation. So that will go ahead and conclude it. And like I said, have a good day.